Assalamu alaikum everyone. This is Fahad Ansari and I'm here to help you conquer chemistry. In this video, we will be looking at relative atomic mass versus relative isotopic mass, two terms you may have heard before but are not sure what to do about them. Before we go on to this video, I would like you to leave a like, share this video, and do subscribe to the channel. Let's begin. So relative atomic mass. It is defined as the average mass of the atoms of an element relative to a twelfth of the mass of an atom of the carbon 12 isotope. Wow, that is a long definition. So let me just simplify this for you. Imagine we have a scale along which we are measuring the masses of atoms. And by the way, on this scale, we use atomic mass units, right? Atomic mass units are used to measure the masses of atoms. Now, on this scale, what we're going to do is we're going to assign the carbon 12 isotope, atoms of this isotope of carbon 12, going to be assigned a mass of 12 units on this scale, right? So if you have a scale on which you have a mass of 12 reserved for carbon 12 isotopes atoms, then you're going to compare the average masses of atoms of elements to this particular isotope's mass. So for example, we have sodium. You can see over here the relative atomic mass given in the periodic table. Now you can see that this is in decimal places, right? The reason is that this is an average mass across all sodium atoms, across all isotopes of sodium. So the average mass of any given atom of sodium would be 22.99. So if I plot it over here, get something like this, 22.99. This will be the relative atomic mass of sodium atoms, right? And as another example, we have fluorine. It has a relative atomic mass from the periodic table of 18.998. So it would be pretty close to this particular value of the relative atomic mass of sodium. We have right below it that for fluorine. This is the average across all isotopes of fluorine. So what is relative isotopic mass? It's basically the same thing, except instead of looking at all of the atoms of a given element, you just look at the atoms of an isotope of that element and then compare the mass of that atom to the mass of an atom of carbon 12 isotope. So same scale, and what we're going to do is, while on the scale you have a mass of 12 reserved for the atoms of the carbon 12 isotope, remember carbon 12 is not the only isotope of carbon. We have two other isotopes. We have 13 and 14, right? And these are the relative isotopic masses of the atoms of the carbon 13 and carbon 14 isotopes. All right, so you can see that the isotopes, the different isotopes of this element, have different relative masses. And if we can put them together somehow, we will get the relative atomic mass across all atoms, across all isotopes of carbon for the element carbon. Now, how do we put this all together? What we do is we find the percentage abundance of each isotope. And this is done using an analytical technique known as mass spectrometry, right? So mass spectrometry is going to give you the percentage abundance of each isotope of an element. It's going to give you a graph of percentage abundance of each isotope versus the mass to charge ratio. Now, I'm not going to go into the details of how mass spectrometry works. That's for another video. But suffice it to say that this mass to charge ratio is just a fancy way of putting it. But normally we have the charge set to +1. So the mass to charge ratio is basically the same as the relative isotopic mass, right? So you're basically plotting percentage abundance versus the mass of each isotope. And you can use this data to calculate the relative atomic mass using this formula. looks like a lot of mumbo jumbo, but we're going to look at two examples just to see how this formula can be used. So over here you can see a sample of element X is analyzed using mass spectrometry. The mass spectrum obtained is shown. Right. So you can see that the graph has been plotted of percentage abundance of each isotope versus the mass to charge ratio, other words for isotopic mass. So what we're going to do is we're going to use that formula to calculate the relative atomic mass of element X. So we have the formula over here. Now what we're going to do is we're going to look at the percentage abundance of each isotope and multiply that by the mass to charge ratio. So over here we have 3 times 112, right? Now we're going to do the same thing for the next isotope. We have 56%, the percentage abundance, times the mass to charge ratio, or the relative isotopic mass of that element. It's going to be 56 times 114. And then you do the same thing for the third isotope. It's going to be 41 times 115. And once you do this for each of the 3 isotopes, you add up the results, right? And then you divide all of this by the sum of these 3 abundance values that you have. So that's going to be 3 plus 56 plus 41. Incidentally, this sum gives you 100. So now I'm going to put this all together. I'm going to calculate, and I'm going to get an answer of 114.35. So 114.35, if you round this up to 1 decimal place, you get 114.4, right? So 114.4, that gives you option D. Now another example. So over here we have an alloy of copper and gold called tumbaga. A sample of tumbaga was analyzed, again using mass spectrometry. The mass spectrum of the sample is shown. Now you can see over here that you have these 2 mass to charge ratio values that are very close to each other, and then this one that is very far apart. So you can tell that these 2 are belonging to isotopes of the same element, and this over here is an isotope of a different element altogether. Now, if you look at the periodic table, these 2 in fact are isotopes of copper, and it says that we need to calculate the relative atomic mass of the copper present. We don't need to worry about the gold. So these 2 isotopes are the ones we're going to use. Formula is here again. So what we're going to do is AR is going to be 56.36 over here times 63. So 56.36 times 63. So percentage abundance times the relative isotopic mass, or the mass to charge ratio. And it's going to be done the same for the other isotope of copper in this sample. And once we have done that, once we have done all of that, we're going to add up these results. And then we're going to divide this by the sum of the percentage abundances. It's going to be 56.36 plus 25.14. Now, this sum of percentage abundances does not add up to 100. That is why I have not written 100 in the denominator of the formula. It's the sum of percentage abundance values. By the way, this symbol over here is sigma, and it stands for summation. And once I calculate this result, I get 63.62, and this is 2 decimal places as asked for in this question, 2 decimal places. So this is the weighted average using percentage abundances and the relative isotopic masses of the isotopes of an element to help you calculate the average mass of the atoms of an element, or the relative atomic mass. So I hope you understood this concept and you know the difference between relative atomic mass and relative isotopic mass and how to calculate one from the other. So I hope you enjoyed this video. If you did, do leave a like, share the video, subscribe to the channel, and I will see you in the next video.